Hello guys, welcome back to Zone African Motives. Still on engineering science and working on it. In this case, we've got the question paper from November 2022 that we're going to be considering on question number 7, where we are given the first part to list two basic gas properties in this case. All right, so whenever we are dealing with gas, that is we have got the isothermal process, the isochronic, and the isobaric. These are the processes that we have whenever you're dealing with gas. But what actually does that part mean, or it actually represent? Okay, so let me just mention this. Like I said, we've got the isothermal. All right, so we've got isothermal in this case. So on an isothermal, it is a process whereby we have got constant temperature. All right, so this is a process where we have got constant temperature in this case. What we need is the isothermal part. Here I'm just explaining what actually it means in this case. All right, we also have the isochoric, sorry, not isochoric, but isochoric process, which is a condition whereby we've got the constant volume in this case. So here we've got the constant volume. All right, and the last part is isobaric. All right, so we've got isobaric in this case. This is a consideration where we have got the constant pressure in this case. So here we work or we deal with constant pressure. So the processes that we are being given, that we are asked, are these ones: the isothermal process, the isochoric process, and the isobaric process. So these are the processes that we have. Just any two of these ones are acceptable in our calculations. All right, so on the other part, we are given on 7.2 that there is a rectangular metal plate of which measures 73 centimeters by 60 centimeters in this case. Okay, so we are given a cross section of a rectangle which is in centimeters, and here we are to calculate the increase of the length in square centimeters. So I'm not going to change this dimension. I'm going to leave them in centimeters as they are. So this is 73 centimeters by 60 centimeters, which is actually area, length times width. So this is actually our area. So it is a temperature of 71 degrees Celsius, which is the initial temperature of 71 degrees Celsius. The coefficient of linear expansion we are already given for the material is 17 times 10 to the exponent of -6 per degree Celsius. Calculate the increase in area. The increase in area, that is a change that is going to happen. If it is a positive, that's an increase. So we need the change in area for this plate in square centimeters. All right, if its temperature rises to 121 degrees Celsius, which means we are now given the final temperature, which is T2 of 121 degrees Celsius. So how can we calculate the change, which is the increase in area in this case? All right, so from the information that we have, remember also from the formula that you're given that the change in length can be obtained from the product of 2 times the linear coefficient of expansion times the original area times the change in temperature in this case, which simply means T2 minus T1. The original area, that is length times width, the one that you're given, the length times width in centimeters. Since we are to calculate in square centimeters, don't change these to meters because already your answer is needed in square centimeters. So just substitute your values as they are. So that means the change in area in this case is going to be 2 times the linear coefficient of expansion, which is 17 times 10 to the exponent of -6 times the original area, that is length times width. So here we have got 73 times 60, length times width. This is for the area, all right, times the change in temperature, our change in temperature, that's T2 minus T1. So we've got T2 and we've got T1 here. We are going to subtract the 2. So that is going to be 121 minus 71 like this. All right, so this is going to give us the change in area which is when it is a positive, that's an increase. All right, so that's why we are given that as an increase, because this is going to give us 7,446 square centimeters. That's a positive, representing an increase in change in temperature. All right, so that is how you can calculate this. If you are given the linear coefficient, then you have to multiply by 2. That's going to be 2 alpha in this case. All right, so let's check the other part of the question, which is on 7.3. We are given the density of a 1 cubic meter mercury. All right, so let's just remove this part here. So here we have got the volume in this case that we are given, the first part, that is the volume, the 1 cubic meter there. So that's 7.3. So we've got a volume of 1.1 cubic meter for a density at a temperature of, so that is the initial temperature there of 0 degrees Celsius is, so this is the density. The density of these conditions is at, that is the density of 1.07. So we have got the density for this consideration, which is at 1.07 times 10 to the exponent of 4 in kgs per cubic meter. Remember that density is simply from mass over volume. Then the volumetric coefficient of expansion. So in this case, we are given the coefficient of expansion as gamma. So our gamma in this case is given as 200 times 10 to the exponent of -6 per degree Celsius. And we are given to calculate the density at 70 degrees Celsius. That is T2. So you've got the second temperature, which is our T2 at 70 degrees Celsius. What is going to be the density at this condition? Just like the previous part where we are given the density. All right. So what you ought to understand is, from the given information that we have here, the density can be calculated if we know the volume, because here simply the density is equivalent to the mass over the volume, the cubic meter, mass over volume. So we've got mass over volume. So we have, if we can have the volume from this part, if we can have the volume which corresponds with the second consideration, which is our final volume, or our V2 in this case, because the first part we are given V1 as 1 cubic meter for this density and this temperature. So meaning to say, if we can be able to obtain this volume, we can be able to calculate the density from there. All right. So how can we do this? From the information that we have, remember that the second volume, which is V2, can be obtained from this formula. V2 is equivalent to the original volume plus the change in volume in this case. So we are going to calculate the change in volume. The original volume is our V1 here. We can just have this as V0, which is our original volume. So how can we calculate the change in volume? If you are dealing with the change in volume, the change in volume is going to work with the volumetric coefficient of expansion, which is gamma in this case. So that means our change in volume is going to be VO times our volumetric coefficient of expansion, which is gamma, times the change in temperature, which simply means T2 minus T1. The original volume, like I said, that is from the given this part here per cubic meter, and we're given a volume of 1 cubic meter. So we can calculate the change in volume from this one, the original volume. That's 1 times gamma, which is our gamma in this case is 200 times 10 to the exponent of -6 times the change in temperature. It was at 0, now it's at 70. So that's T2 70 minus 0, like this. All right. So the change in volume is going to be something like, all right, so this is going to be 0.014 in cubic meters, because this was cubic meters here. So that means we can calculate V2. So by finding V2, all right, let me find V2 first before I explain this. So V2 is going to be the original volume, which is 1 plus the change in volume, and our change in volume here is 0.014. 0.014. So we are going to have our V2 of 1,014 in cubic meters. So remember, why am I to calculate this? Because I said density can be calculated from mass over the volume. So if we can calculate density from mass over volume, it means that we are going to take the mass that we are given. In this case, our density is going for the second part. So our density is going to be the mass over the given volume, which is our V2 in this case, the one that we calculated from this part here. So where do we have the mass in this case? Remember, from the first consideration here, I want you to be very, very careful on the mass. We are given that per cubic meter here, per a cubic meter, our mass is 1,07 times 10 to the power 4 kg per, remember, it's mass per volume, mass divided by volume. So meaning to say here, we have got the mass from the density here. We are given the mass of 1.07 times 10 to the power 4 kgs per each cubic meter, and we are given a volume of 1 cubic meter. So which means when our volume is 1, this is the mass that we're going to have. So here we are going to have our mass as 1,07 times 10 to the power of 4 over the volume. Now has changed due to the conditions of what? The change in volume. We are now having our V2 as 1,014. So this is what you're going to have. So if we divide mass and volume, we obtain density. Remember, this is mass, which is in kgs, and this is volume in cubic meters. So our density in this case is going to be, we are going to obtain something like 1,0552,268, which is in kgs per cubic meter in this case. All right, so we can even write this in other ways, like you can multiply it to times 10 to the power 4, whatever that you want, or you can just simply leave your answer like this. All right, you can simply have your answer for density like this. So this is the density that you're going to have at the second temperature, or at the second condition that we are given in this case. All right, so like that, guys, we've got 6 marks. So here the major part was on finding the second part of the volume from the change in volume. Then we calculate the final volume. So V2 is simply representing VF, which is our final volume. So VF is original volume plus the change in volume. All right, so 7.4, we are now given this part. We have got a copper. That's a copper, a circular copper disc, which has got a radius of 22 of 0.44 at 22 degrees Celsius. So all this was on linear area and volume expansion. That was what we had on this question 7 on this question paper. Okay, let's see what we have. So this is a circular copper where we are given the radius. So from the radius, we can have our diameter. From there, if you multiply by 2, we've got diameter here, which is 0.88 meters. So we've got the diameter, and the initial temperature in this case, which is T1, is 22 degrees Celsius. The linear expansion coefficient of copper is, we are given alpha for copper, the linear, which is 17 times 10 to the exponent of -6 per degree Celsius. Calculate the increase in diameter. Take note, we need the increase in diameter. How is it going to change? If the final temperature is increased to, so the temperature is now at 84 degrees Celsius, which is our T2, 84 degrees Celsius in this case. All right, so how can we calculate the increase in diameter? Definitely, here, this is a circular copper. So from a circular copper that we have, this can give us an area. So we can obtain the original area from this part. So in order for us to have an increase in diameter, it means we are supposed to calculate the increase in area, or the change in area. Once I have the change in area, I can calculate the change in diameter, because I know that area is simply equal to pi d squared over 4. So here, if this is the change in area, this is going to be the change in diameter. So that's what I need. So I need the original area in order for me to obtain the change in area, since we know that the change in area, which is the increase in area from the linear coefficient of expansion, it is going to be 2 times alpha times the original area times the change in time in this case. So here we are obtaining the area expansion if we multiply by 2. So we do not have the original area, but we can calculate this because we're given the diameter from the radius that you're given. So our original area is going to be pi d squared over 4. So that is pi times the original diameter of 0.88 squared over 4. So this is going to give us the original area. So here, if we are to simplify properly, our original area is going to be something like 0.608 square meters if you round off to 3 decimal places. So that's our original area here. So like I said, in order for us to have the change in diameter, we must have the change in area. So we are going to have the change in area from this formula. Our change in area, that is 2 times the linear coefficient of expansion, which is 17 times 10 to the exponent of minus 6 times the original area that we got here, which is 0.608 times the change in temperature. Remember, I said this before, that's T2 minus T1. So that means in this case, we're going to subtract T2 minus T1. That is 84 minus 22. All right, so this is going to give us the change in area. So the change in area, which is going to be something like 1,282 times 10 to the exponent of minus 3 in square meters. All right, so this here is the change in area. Take note, guys. We have a change in area, not the original area. The question is for us to calculate the increase in diameter. That's a change in diameter. So from the change in area, we can calculate the change in diameter from this formula that I was saying here, to say that the change in area is going to be equal to pi times the change in diameter squared. So this, we can use our formula, substitute our values then, or we can just make this the subject. If we cross multiply, that's going to be pi d squared is equal to 4a divided by pi here by pi, so that you can make d the subject. So d squared is equal to 4a over pi. So you can introduce the square root. So d is simply equal to 4a over pi under the square root. All right. So this here is representing not only just not just a normal area, but a change in area. So this is no longer just an area, but it is the change in area that you're talking about. And also this is no longer a normal diameter that we're talking about. This is a change in diameter that we're talking about. So this is going to give us the change in diameter. So therefore, our change in diameter is going to be the square root of 4 times the change in area, which is 1,282 times 10 to the exponent of minus 3, everything over pi. So under the square root, we are going to obtain a change in diameter. Having our values in square meters, that means our diameter in this case is going to be in meters. So that's 0,0400 and so on in meters. So if you round off to 3 decimal places, our change in diameter is going to be 0,04. The 0 here is not going to affect, so that's 0 here in meters. All right, so that is what you're given in this case. If the question was to calculate the final diameter, or the final part, the final diameter, you use the final area, which means you're going to calculate area 2, which is our area 2 is taken from the original area plus the change in area. From the area 2 that you have, you can calculate D2, but here you are asked to calculate an increase in diameter. An increase is a change in diameter. Why are they saying increase? Because the change in area, it's a positive, so that means it's increasing. If it is a negative, it's decreasing. All right, so that's what we had, guys, from this question 7.4, having a total of 5 marks, and everything on this question a total of 15 marks on hit. So these are the typical questions that you might be given. For more questions, let's keep on revising from our past exam papers and also videos from Maison African Motives under playlist for engineering science N4. There are so many things that you can learn from there, which helps us in our revision as we are preparing for the exams which are ahead of time. But for now, that's it from Maison African Motives. Till we meet again.